problem solving leading to explorations. And part of the thing was when we were discussing the workshop, how can you have a workshop for mathematics teachers and not have a problem solving session, right? So, there are a few things that I do want to say and not hopefully belabor the point is that one great problem for me in mathematics education is that problem solving is reduced to end of the chapter exercises, right? I mean, end of chapter exercises are important in teaching, learning, I presume, but it's not the same thing, right? That problem solving is about not applying a particular formula or checking whether one understands a particular formula or a particular technique, but about solving problems, right? Now, Halmos, in a famous quote that I like very much, asks, what is mathematics really about? Is it about definitions? There are these famous definition of dimension, right? Is it about theorems? Is it about proofs? Is it about techniques, methods? What is it really about? And then, in fact, he has a long list. Is it really about this and so on? And then he says, all this is important for mathematics. But if you really ask me, mathematics is only about one thing, and that's problem solving. It's the raison d'etre of a mathematician is to solve problems. That's what it's about. And to solve problems, you may come up with various techniques and so on, and you come up with definitions, you come up with a lot of beautiful things, but really what you want. Now, how much of that taste that we have that we bring into our children? And I think this is all that I would like to say. Now, we had this discussion before lunch, and I'm aware of the pressures of syllabus, board exam looming large. Of course, in a board exam, you don't sit and solve problems. You answer questions, right? You don't do problem solving in an exam-oriented situation, right? But what is that? And most importantly, what are good problems? What are bad problems, right? Is there such a thing, right? We talk about hard problems and easy problems and so on. But I'm really interested in what are good problems and what are bad problems. Anyway, so, and I'm sure, and these are things that I think we can make up our minds on and not necessarily agree, right? That's no problem. There are some problems that I consider good problems. So, but are there ones that we all consider, which we like? Why? This is something I think we should think about, and I'm afraid we don't get too much space for that, right? So, this is also something that I would like to suggest that we need more fora for sharing problems, grading problems, discuss problems, right? Problem posing, right? Now, I'm part of Tamil Nadu Science Forum, and once we had this very interesting exercise in Tulir, which is a magazine, and through Tulir, we gave a call for problems, and we were talking about middle school mathematics, took up some units. This is not board exam, right? So this is middle school. And then we asked for what would you consider, suppose all, we wave a magic wand, no CEO, no DEO, no whatever management. Just ask, let's just have what are the most interesting problems that we would like to do in class with our children, right? And then we ask for submissions. And most of them, a huge part of it turned out to be end of chapter exercises, right? So, illustrative of teaching some concept, right? But rather than problem solving experience for children. So, I'm making all these remarks to say that we don't get enough training, enough discussion on problem posing, and most mathematicians would say good problems are those which, when you solve them, lead to more questions, right? So, if at the end of solving a problem, there are some natural questions that come up, that's a very good problem in my opinion, right? And in the process of solving them, you can generalize, you can extend, you can explore. So, somehow problem solving as a way of exploration probably is the most important thing that, well, there are many mathematicians who have talked about. Polya has, talked so much about it, various kinds of problems. If you have seen Polya, he talks about 4 kinds of problems. MF problems, def problems, and motivation forerunner. Well, there is one more, but actually definition, I'll put this along with that. So MF problems are motivation and forerunner problems. He says even before you start a topic at all, you do some problems. All the problems do is to motivate the subject, motivate the topic. So he calls it forerunner, and then there are forerunner problems where you get a taste of what is to come. You may not quite understand, you will do something simple. And then definitional problems. We don't do these at all in general, and even in university I find we don't do too much of that, where you change the definitions a little bit and see what happens, right? You define something, I mean, morning somebody mentioned determinant, right? There's this weird creature called determinant that we define. Okay, you talk about matrices, somehow you change sign, you multiply this, and you get a number. What if I don't, do this -1 to the n, right? What will happen? Call it something else. It's called something else, but let's not worry about it, We'll call it something, what happens, what does that number indicate, like that. So, and then there are exploratory problems. Exploratory problems are very important for Polya, sets up many. And then finally he says, DAD problems. DAD problems are direct application and drill. I like that term. Direct application and drill, right? What is a drill? You blow a whistle, hands up, hands down, apply this formula, substitute, And we do a lot of these DAD problems. And they have their importance. So this is one thing that I also want to say that, when we talk about creativity, exploration, and so on, I think one should not undermine these. One needs a lot of practice. Direct application and drill is also important, but you need a mix of all these, right? So we don't get much space for these discussions. So I want to talk about some very, very simple problems. So I didn't pick up anything from any particular syllabus. So one problem that I mentioned in the abstract, right? Something very straightforward. So what is that? So there are two people. I just unimaginatively call them A and B. So A sums up to, what was the number that is given? Sum n. And B sums from n plus 1 to 20. So they both calculate the sum. And these two turn out to be equal. So the question was, okay, is there such an n? What is the n? So how do we go about it? What do we do?
Start with smaller numbers of n.
Is that okay? Fine. Smaller numbers of n, remember n is ranging from 1 to 20. Yeah. So that's one suggestion. What else should I do?
Call some A and some B.
Okay.
Both the sums, you add.
So
Basically, equating, we need the equalized part of both.
right. So
Call both of them A and B and then equate them.
so there is some A and some B, and these two are the same. Okay. What should I do?
Add summation n to both.
Add summation n to both. What will that give me?
So I get a convenient sum on the right hand side as well as an expected sum on the left hand side.
I see. Okay. So this is another suggestion. Anything else? No. This is usually what happens with problem solving, right? You come across a problem. We need something that we need to click, right? Okay. These are all suggestions that we can explore. Any more? I just want to hear. Sorry, okay, what for this particular one, for this problem, tell me. Arithmetic progression, okay. Sum of 1 to n is n into n plus 1 by 2, okay. But we don't know what n is. Here is n into n plus 1 by 2. But then here is an n plus 1 to 20. Yes. I'm sorry? Okay, here is one suggestion which says sum, let's take the entire sum 1 to 20. One second, it seems clear, right? When you take the sum of 1 to 20, just one moment, what is that? What is this sum? 210, right? Now we know that they are both getting equal, right? They are both getting equal numbers. So what is the sum that they must be getting? It must be 105, right? A must be getting 105, B must be getting 105. Then only you could have, right? So we have got n into n plus 1 by 2 equals 105. So n into n plus 1 is 210. Therefore, what do we know? What is n? 14. 14 times 15 is 210. If you want to set it up as a quadratic equation and do the factors, and right, you will get what? N plus 15, no, n minus 15 times n plus 14 is the factorization you will get, and therefore you will get 14, right? So you get n as 14. Great. So we were trying many things, and among the many suggestions, one suggestion immediately gets you, right? So this is usually the situation with the kind of problems that we are looking at. But what about asking more from here? That's what I wanted to. In the abstract that I was asking, what else can you ask? Suppose you have solved a problem now. We are happy that A was summing up to 14 and B was summing from 15 to 20, and they both got the right answer, and we figured it out, right? They got the same sum. What next? Okay. So this, yeah, where is that? Yeah, sorry.
Restricting from 1 to 20 is give them liberty to give a
General formula for what?
Just restricting the sum from 1 to 20.
Mm-hmm.
Why can't they go beyond 20 and then come back?
So you can go up to, let's say, k, right? And right, so your one person is going from 1 to n, and the other one is going from n plus 1 to k, or m or whatever, and then you can do. Okay. Now there is a lot that you can do. I have some questions that I have written down. I want to hear more. What else? This n into n plus 1 by 2 itself we can look at. What is this, right? And okay, so why is it clear that when you do this, you are always going to get an integer? Let's something obvious, no? N into n plus 1 by 2. Why is it an integer? Because it's, yeah, okay. And one of them is even, and therefore maybe we can look at this. Well, we all know this picture, right? What is this picture? I am adding, how many dots are there? And so on, right? So what is this picture? I am just putting some number of dots. Yeah? I heard something that I did. Some of the first 5 numbers, right? So if somehow I can do this, I don't know how far n dots I should put, but yeah. So this is really the number of dots in this triangle, right? But let's leave it at 5 for the moment. Hopefully we can see for n, right? So this, if I fill up, suppose I fill up like this. Have I drawn it correctly? Yeah. And 5, I need to have one more to make it. Yeah. So then I realize that I have divided it exactly like this, right? I have made it a 5 by 6 rectangle, and the number of dots that I have got in the lower triangle is exactly half of that, and so I can write this as 5 times 6 by 2, and in fact I can do the same thing with n, right? Okay, so this suggests that this sum I can actually write as n times n plus 1 by 2, right? Now you can give a proof of this, the sum of the first n numbers, you can set it up by induction, or you can do a picture like this. Actually this picture is even better in my opinion, because you look at it and immediately it's kind of obvious that it should be. But can be given, maybe, I hope somebody will be unhappy with the proof through picture, because it's nice, but maybe my picture something was wrong down there. How do I know? What about, is there an algebraic expression that I can write and from this picture argue that in fact it must be n into n plus 1 by 2, right? Can I give a proof from these? We can do that, but let's call this number Tn, right? So these are, let's call them triangular numbers. So Tn is n into n plus 1 by 2. So what have we got in our little problem that we were looking at? We actually had two numbers, Tn and Tm, such that Tn is actually equal to Tm by 2, right? Both were triangular numbers, right? This is 1 to n, and the other one is 1 to 20. 20 happens to be m here. So we had triangular numbers Tn and Tm such that Tn is actually equal to Tm by 2. So we have found two triangular numbers, right? One multiple of the other. T and 2t, both are triangular numbers. Now what about this? Are there triangular numbers? Are there numbers, or is there a number? Let me write first. Is there a number t such that t, 2t and 3t are triangular numbers? What do you think? We have shown that you can have triangular numbers t and 2t. What about, I want a number t such that t is a triangular number, 2t is a triangular number, 3t is also a triangular number. What do you think? Any? How do you proceed? What about, of course, I won't stop there, right? If you say something, I'll ask, what about t, 2t, 4t? There are certainly infinitely many triangular numbers, that's no problem, because each n is going to give you. But among them, what kind of things that we can see? We happen to accidentally come upon a t and a 2t, both triangular numbers, or is it something more that is going on? So here is one. I'm not going to go further in this. Actually, I have another 5 questions of this kind, right? So I'm just saying that that little problem can take you further down, and in fact, even the algebraic proof of this is fun. And in fact, if you want to explore further, you will need those algebraic proofs, right? You will need some notation. At this point, you must write things like sigma equal to 1 to n I, or if you have in general some sequence S1 to Sn, then you have to bring in notation, and we have to look at simplifications like, well, this picture suggests that if I've got right, can I take from that, and this is n into n plus 1 by 2, can I derive the formula? Ask lots of questions, right? So I am saying that even in the things where one part of it is that you know the answer and pose many things that you can. Another is where you don't know the answer, pose and explore. You can go much further. There are maybe one among the questions I've written down. This I think should be interesting. Okay. So we had this problem with which was running up to n and then n plus 1 to m, right? This is the problem that the sum is the same, right? So here is a nice problem to solve, something of this kind. Suppose n equal to a, m equal to b is a solution. In our case, n was 14, m was 20. Then show that then so is I put m equal to a, right? Yeah. N equal to 3a plus 2b plus 2 and m equals 4a plus 3b plus 3. Okay, this is a nice problem. And this suggests that you are looking at not only the particular problem and we were solving that, but can I churn out solutions of this kind, right? If you're going to get one solution from that, can I generate the next solution? Of course, this is a closure condition, right? Once this is a solution, that will generate more, and so on. So you will get infinitely many solutions to problems of this kind, right? So it's not a formula, right? It's not a formula like I think you were talking about, right? So for n and m, but at least if I can get a solution, I can tell you how to produce more and more solutions, right? So this little problem is already capable of taking us in many different directions, right? And this is a problem that I picked up from some book. It's not as if, it's not an Olympiad problem or, considered a fairly simple problem, right? An exercise in this. Let's do a couple of more. Any comments related to this? Anybody else wants to say something about this problem? More questions that we can ask? Sorry? T, 2t and so on, and what? T, 2t is certainly possible, we have got. You mean an infinite sequence like that? Well, I just asked whether you can do t, 2t and 3t. So, well, try. You can write to me. I want to hear more on this, what you have got. Right? Okay, so I want to move on to just a couple of problems. I'm not going to do very much, but just to illustrate some way of how we might do things. So here is a problem. There are 4 different lines, 4 straight lines are drawn on a flat piece of paper on the plane. And their points of intersection so let me call it pi are counted. So what numbers are possible? As this count that we had, as the count. I have just drawn 4 lines on the plane. Then this is also a solution. 3a plus 2b plus 2, 4a plus 3b plus 3 is also a solution. Yeah. If n equal to a, m equal to b is a solution, then so is. M is equal to, so the first number n is 3a plus 2b plus 2. The bigger number is 4a plus 3b plus 3. Huh? So this is n and this is m. Sorry, it's the same problem. A is summing up to 1 to n, b is summing from n plus 1 to m, and they get the same number. So that's the problem.
We can frame the questions of the solution of any type, or
No, you can do whatever you want. I'm just suggesting that, that's my whole point, right? We want some exploration, right? I'm saying we want to, rather than stop with solving some problems, we don't have these chained exercises, right? And that's what I'm pointing out. The more chained exercises we have, right? I mean, and for God's sake, not for the exam, because in the exam it's much worse. Because if you've got a problem based on a problem and problem based on many, it's very nice, but if you lose the first one, you are dead, right? So not for exams, right? I am talking about classroom, right? So this one, at what level will we say this problem? Just finding the 14 and 15? Middle school we can try. The formula, maybe not. Coming up with, looking at the picture and figuring out the pattern, saying n into n plus 1 by 2, middle school. But seeing that as this, I put a sigma, yeah. And what are we talking about? All this, is that correct? What is the right expression? Which should it be here? Should I put in? How do I manipulate? This is all later. This one, trying to even understand what this means, trying to understand this. So let's not worry about stages and levels and so on, right? This is my point. At some point, we should be able to engage with the problem, because there is a problem to solve, and in solving the problem, something starts happening in our head, we can start thinking more, we can start discussing more, and we need some things to which we don't know the answer, right? That's my point. And some things which we know, like for instance, I am giving you this having seen that this works, right? So we need all of it. We need all of it. We need a combination of all of these. But what I'm pointing out is that for exploration, right? So exploration based on mathematical topics is very nice. It's very important. Like tessellations, which I like very much, and Shashi does a lot with also, right? Platonic solids he was mentioning. Topical explorations are very nice and very interesting, one should do. But I also like explorations that start from little problems, right? There are lots of problems, and if we can each have a diary of 10 problems that we like for that reason, and say that, I like this problem because of this, right? How about this? And say, I'm terrible with problems of this kind. Maybe this is a problem that I like, right? That's good, that's great. And if our children start doing that, I think we don't have to worry about fear and all these things, right? Because we can explore. So I just want some. So here is another problem here. What is this saying? There are 4 straight lines, and as I said, on the plane. And now I'm counting their points of intersection. I have no idea, right? I want to know how many points of intersection can you have? 0? 0? How? 4 parallel lines, right? Okay. So 0 is easy. What is okay, let's see. 1 point of intersection. How does it look? So 4 lines and 1 point of intersection. I'm really bad at doing this. Yeah? So this is 1 point of intersection. That's easy. What about 2 points of intersection?
Only 2 lines are right away. No, 1 line is intersecting the other.
Whatever. Not possible? Let's go over to 3 and then come back to it. So 3. Yeah, 3 parallel lines and 1 cutting across. That's fine. What about 4? Yeah, maybe like this. This 4. What about 5? That's what I started drawing, right? Yeah? Okay. So this is clear. With up to this, it's clear. What about 2? Let's get back to 2 now. Right? It so happens that 0, 1, 3, 4, 5 are all immediate. What about 2? So 2 is not possible, somebody said. Yeah, so what is the argument? Give me a proof. Remember, my flat piece of paper is infinite. It stretches all the way on the horizon. So if there are 2 lines which are not parallel, what do you know about them? They're going to intersect at some point. There will be a point of intersection. So let's argue about these two lines. I mean, the case where did I put this there? There are 2 points, right? So let's call these points of intersection P and Q, right? Now I want 4 lines, 2 points of intersection. So there must be at least some line passing through P which is different from PQ here. There must be some line. Let me call it L. Now our friend Q also must have some line passing through Q, which is not the same as that. These are 2 distinct points of intersection, P and Q, right? So P is not the same as Q. So and if so, there is some line passing through Q, but what kind of line is it? Should it be parallel to L or need it not be parallel to L? If it is not parallel to L, let's call this line M. I'm sorry, it has to go through Q. So this should also be parallel to L. Otherwise, there will be a 3rd point of intersection, right? Now we are ready to look at the line joining P and Q. Let me call it N. Now we have got 3 lines already. What about the 4th line? If the 4th line passes through P, what's the problem? That will get, yes, so that's going to give you another point of intersection with M. The 4th line passes through Q, I'm going to get another. So the only lines that you can have are L and M themselves. So the 4th line has no place to go, and that's it. So we have proved that 2 cannot be a point of intersection. I mean the count. 2 cannot be a count of points of intersection, right? So I think it's a very nice problem, simple problem. I don't know what stage you will do it. But okay, now my interest is all in what is the next question you ask. It's a nice problem, we have solved it nicely. What's the next question to ask? Otherwise, why should I talk about this problem? Yesterday Balaji said no, small steps, small steps. What is the next as small steps? 6, exactly, you know. You are like, we should be like thinking like children, right? So we said up to 5, what about 6? So 4 lines. Six points of intersection. How would you do? Do it. I am not going to do it. It's a natural question to ask is what I mean. What about 7? Is there a maximum? For count of PIs with 4 lines? If yes, find it, otherwise prove that there isn't. And in fact, I would like to be kind to my children and in fact say that 6 is the maximum. Show that you cannot do it with more than 6, with 4 lines. Again, I am not doing the solution, I am sure some people are thinking about it. This is a nice further exploration to do here. First, think a little bit about it, because it's not easy at this point, right? At this point to even realize that there is a maximum, that you can do it with 6, but 7 is hard. Is 7 hard because of my stupidity or whether it's not possible? At this point, in this particular case, I would say the thing is to actually say that, yes, it actually is not possible. Let's try to find a proof. We've already done a proof, and that's why. One is not asking for doing it without. So there is some style already established, so one can try. How would it be with 7 points of intersection? What should be the situation? And one can actually do this. But again, the reason I am doing it is there is a natural third question there. What is the natural third question to ask? Having done, if you do 1 and 2, small steps. Small steps. 5 lines. For 5 lines, what are the and this again you can fill up pages, right? You can fill up pages, you can draw things, you can try out many things. That's what I would like, right? I would like problems where you can try out lots, right? Go to the board and draw, right? Then you can, really enjoy the exploration. And this is something that I guarantee to you that, okay. Yeah, so, and then of course to ask, for n lines on a flat this thing, you want the number of points of intersection as a function of n. That's not easy at all, but that's what exploration is about, right? In my opinion, one should, and they're not, many problems have the structure that you can push a little more, right? Until you, and this idea of generalization and extension, right? These are two beautiful words that mathematics gives us. You extend the technique, right? When I am looking for this question is an extension, right? I have done all these things for 4, got some experience, now I do it for 5. This is a generalization, and generalization is the stuff of mathematics. And it's not always possible that you create new mathematics in the thing. It may be difficult. It's okay. It's okay to say, okay, this is something I'm going to stop at this point. Of course, in this case, you can actually do it, but some nice combinatorics is there. But my point is that many problems will get you to that thing where after which pushing is hard. But that's when you stop there, right? And backtrack, right? And often this progression is not linear. There are many different directions you can explore, and you can backtrack and try something else, right? And so there are lots of such problems. So I'm going to take one more in the given, well, at least one more. Yeah, please. Yeah, that I hope somebody will say. Can you just repeat what you said?
No, I'm saying a problem like what you posed doesn't take more than 5 minutes from a class and yet changes the nature of the whole class.
Right. That's what I would like. Right. I mean, so I am once again, as far as possible, I am going to mention only problems that are very simple and very easy to solve. I am not talking about tricky stuff. This is not the tough stuff that will work in Olympiad at all. I am not talking about problems of that kind. These are very simple things, but things where every child can have a go at, right? Hopefully. Everybody can try something, hopefully can talk, the kind of thing that Shashi was talking about earlier, where there is some discussion, some people sit in groups and try out, argue, hopefully can argue and say this is wrong, or like Balaji was saying yesterday, children love it when you say this is wrong and then know why am I wrong? I mean, try to, right? What I'm saying is actually correct, trying to argue like that, right? So that's so here is another problem. This is actually something that I actually found in a textbook. So it's a textbook problem, but it was done for a particular purpose in the textbook. I'm going to slightly subvert it. I can't read my own thing. Okay. So here is a triangle. Its 3 sides are given as 10, 22, and y, and the area is given as 83 square units. Find y. There are several methods that you can apply to this, right? I mean, when I've drawn it, especially like this, right? I mean, you don't usually draw it like. I mean, by the way, children, when they draw triangles, they always draw with a, right? There should be a flat. I mean, a triangle cannot be rotated this way. It should be like this. And in fact, I think in middle school, for many children to figure out that there are triangles which are not equilateral takes some time, I mean, right? So every triangle, so scaling triangles are a bit bizarre. Anyway, so let me draw it like this. I hope you won't object. So one standard thing is to drop a perpendicular, right? I mean, this is a sort of one canonical technique, right? What is the advantage of that? So let's give them names, right? So this is another thing. The triangle is just drawn like that. We have to give it some name. Name the triangle. P, Q, R, let me call it N. And this is 22. And I dropped a perpendicular. Okay. Now I can give some name to this. Does that help? Yeah? I'm sorry? Half BH is 88. B is 22. I mean, I have, oh, by the way, the book had horrible numbers, so I have put in some friendly numbers. So that's another thing I don't understand at all. Why is it that many problems use horrible numbers, right? So I don't know why, and we then get into a calculator is allowed and not allowed and so on. Anyway, so in this problem, it's a complete distraction to get into computation, right? So we might as well, right? So what is H? H is 8, okay? Then let's proceed further. So next you can find Qn, right? Qn squared plus H squared equals 10 squared, right? That's the correct. And then you can find Nr, and then from that you can find Y. Yeah? Yeah, I'm saying the moment you see, so the only thing that we did was really to say drop a perpendicular, right? Drop a perpendicular. After that, like machine got to work, right? The machine immediately says, area is half BH, right? And from that, B is given, so I can find H. And then this is a right angle triangle, so H is given, hypotenuse is given, so I can find this. Then I can find the remaining one. From that, I can find Y. There is something that's going on. There is one whole sequence that is triggered off, right? But what other point of, so it depends, that what is that particular flash that we saw that started with, right? That happened to be drop a perpendicular. What other thing you could be doing? I mean, I was doing this. I found at least one child who said, and somehow I had thought in this problem, couple of these I have tried a few times, so that is what I'm saying. So I thought this is the most natural thing, and I expected this everybody would say. But I actually met one child who said, oh, area, it's half AB sine theta. Area is half AB sine theta, right? If you have an angle theta and the sides that make the angle are A and B in that triangle. So let's call this so 88 equals half times and all this if you do, sine theta works out to be 4/5. right? Because 88 goes 4 times, 22 4s are 88, and then I have got a half and 10, right? What do I do with this? How do I proceed? I am looking for y. Find cos theta, exactly. So, from this, find cos theta, and then the cosine rule, right? The cosine rule will tell you, what is the names I have given? PQR, right? Then, what else can I do here? Yeah, that's it. So, y squared equals pq squared plus qr squared plus minus 2pq cos theta, and solve it, and you get y. A second method and a find method, all because somebody said area was given, area is half BH. Another thing where somebody said area half AB sin theta, perfectly fine. Yeah.
Draw a line parallel to the side whose measure is 22, and you get like 2 possible values.
Very nice. I have seen this also. I have seen this also, and this also is another heuristic. See, there are many heuristics, right? What works when is something that only experience teaches, right? Because in some of them, the experience, the heuristic can lead you all over the place. Yes, this is also very nice. Any other? Heron's formula. This is something, okay, this is the second time I am doing with teachers. I have done this with children. With children, I never got Heron's formula. With teachers, I always get Heron's formula. So Heron's formula, right? Now, and that's also very interesting, and because Heron is somebody to talk about also, right? 1st century AD, Alexandria, who did, I think he did pneumatic drills, he did steam turbines, all kinds of things. And there is a little book called Metrica, I think it's called Metrica, somebody can correct me, where he actually gives this formula. So Heron's formula is very nice, because if you just have a triangle with 3 sides ABC given, in fact, I would think that for the trained people, the first thing that should hit you is Heron's formula, right? Because the area is given and 2 sides are given. Why? I think teachers have to explain to me why is it that children never think of Heron's formula, they are always thinking of these things, right? I mean, maybe some children do also, it's just that from what I have seen it. But at this point, what are the things that we can do? And in my opinion, having seen these, we need to have a bunch of problems in which all these techniques are useful, right? We need to try out all these methods, rather than do one. If, in fact, in a class where somebody says drop a perpendicular half BH, you should do half AB sin theta. If somebody says half AB sin theta, you must do this. And if somebody says both, you do Heron's formula or the other way, right? And can we do, and this is one thing that we talked about earlier. Also, one problem in mathematics is always that one right answer, but even more of an imprisonment is if there is only one method, right? When you have got many methods, it's really liberating, right? When you can try many things, you are less afraid. I mean, you can try out more things after all. So that's all I wanted to demonstrate in this. But after this, there is something to do. There is something to follow. Derive Heron's formula from this is a very nice exercise, right? Or derive Heron's formula from the law of sines, the law of cosines, all these come into play, and it's, in my opinion, when you do it by 3 different methods, it's important to show that you are doing the same thing, right? That these are interderivable, okay, from the, okay, I am only saying derive Heron's formula from this. Do the other way also, you can try, but it's much more at least with children, this is what I would recommend. But these things are all what? I mean, it's a matter of just our playing around, getting some feel for what we think is the right way to go about it and trying it out, right? So, and once again, let me re-emphasize something that we talked about before lunch, is that we are not all good at everything, right? It's perfectly natural for some children to like some problems, take to some problems, and be terrible at some other problems, right? No, there is no such thing. I mean, if you're, I don't think, I mean, well, there are good mathematicians sitting in the audience. I'm sure, we're all not good at solving every problem, right? I know that I'm generally like, have no problem with problems in combinatorics. You give me calculus, I'm always a bit, it's okay, right? Everybody has their things, right? So with children also, I'm saying, what we are really looking at is, hey, unexpectedly, you are showing interest in this problem. You are showing interest in this problem. I thought you were not interested at all. You are showing interest in trying out this. That's what we are looking for. Somewhere, if some spark is like that is possible, we want to give more and more things for further exploration. Here I've got something, I don't want to go further on that. By the way, I would also like you to tell me what hints you will give. Because this is also very important. Not just about designing problems, but give a problem and give a hint. When do you need a hint? And for instance, when I say derive Heron's formula from this, what would be a good hint? Use Pythagoras' theorem. Okay, that's a good hint. What about the second one? Huh? Cosine. Use the formula, law of cosines. Okay. Yeah. They're still a bit abstract for my liking. That's good. I think these will help. But I think you need a little more concrete hints. But it's, there is no golden rule in this. Huh? Whatever works with children is what. And yeah. No, I don't want to go further. So let me take up one more quickly. So one more problem to illustrate certain things that I'm trying to explain here. This is also a textbook problem. So there is a triangle PQR, and there is a circle, as you can see it touches the triangle at three places, U, T, and S, and draw a triangle from these. Now, these angles are given to be alpha, beta, and the triangle inside is gamma. Find gamma in terms of alpha and beta. As I said, this I found in one textbook. How do we go about this? So what are the things here given? Let me get rid of the other things. I'm sorry? Yeah, okay. Don't rush to the answer, right? We want to discuss how the answer comes about, right? I mean, what are the things? That's really what we are after. Yes, something like that. But one thing is to guess and verify, right? I like guess and verify. Many this thing you can actually make a good guess, and that helps you. In fact, in worst case, you can always write the guess and hope that it's correct, right? So that's always there. So it's good. But otherwise, so how do we use all this information, right? There is a triangle and the circle is touching at these places. So that means what? Tangent. These are tangents, right? So PQ, QR, RS, RP, PR, whatever, are tangents. Tangents to to the circle, okay, touching at u, t, whatever. Now, I know that two tangents from the same point for instance, if I look at QP and QR are coming out of the same point and they are both tangents to the same circle. So, what do we know about the sides? They are of equal length. So, I know in particular QS equals QU. Yeah, two tangents from the same point, I'll just write it as are equal in length. You'll forgive me for writing like this. Yeah. So, QS equals QU. So, what do I know about this little triangle? It's an isosceles triangle, right? So, QS and this is alpha. This side is the same as this side. So, I'm sorry, it's not theta. So, alpha plus angle SQ, oh, U and S I have, UQS plus QUS and QSU equals 180, right? So, I know that one of these angles is half of 180 minus alpha, right? So, this angle is half of 180 minus alpha. Now, notice that this side is entirely symmetric. Whatever argument I had on this side, I can apply. So, what do I know? I know that this angle is half of 180 minus beta. So, now I know that half of 180 minus alpha plus half of 180 minus beta plus gamma equals 180. You simplify, gamma is half of alpha plus beta. So, your guess was close, 180 minus and all comes, but something else. Yeah. You can approach it in, that's what I want, at least 3 different ways. I have got 3, hopefully you will give me a 4th. Okay. Yeah. Yes. Yeah. Wonderful, wonderful. So, I love that. That's a very nice proof. That also I have here. And yeah, it's so here is another argument. Yeah. So, I start with the triangle PQR. Now, take the center of the triangle and draw a line. Whichever, let me just take, right? It doesn't matter. And consider, so let's say that, what did I call this? This is U, this is S, and let me call this V, this point. Okay, so, oh, okay. So, what I am using is, see, this is alpha. This whole thing is alpha. Now, what I can look at is that you can see that these two triangles are congruent. This triangle is congruent to this triangle, right? Therefore, this has to be alpha by 2, half of alpha. This angle is half of alpha. Once again, this you can use the same argument now to show that this triangle UQV is congruent to VQS. From that, you argue that this is 90 degrees. Once this has got 90 degrees, this is half of alpha. What you are going to get is that this angle, which is the remaining one, is what we just saw, half of 180 minus alpha. You can do the same thing on the other side and get. Okay. Why did you come and draw? Come. Yeah. So, I thought this is what you had in mind, but here is one. Yeah. Let me give you the, here is a, yeah.
I'll take the same figure.
No, come here. No, draw another.
90%. You've done 90% here. This is John.
Yeah.
So this is alpha,
Hmm.
and this is 90, and this is 90.
But that's what. No.
This is circle.
Okay.
And this is tangent.
Okay.
So this is perpendicular tangent. So this will be 180 minus alpha.
Right.
So and this will be 180 minus beta. So now you're getting this angle is 360 minus pi plus beta.
Excellent. Excellent. So let's give him a hand for this.
Let's circumscribe this. This is alpha plus beta, this will be alpha plus beta.
Same thing. See, once you, it's always in each of this, there's like one key observation, right? After which the machine moves, right? So, yeah. In fact, there is one more. There is one more. In fact, notice that, so here is another thing that we can make use of. Look at these, look at this triangle and look at the chord here, right? There is this, what is this? I think it's called alternate segment theorem or alternate angle theorem. Which says that if you take the angle between the tangent, right, to a circle and a chord, that is equal to the angle subtended at the circumference. That is gamma here. So I know that from this theorem, what can I write? I can write angle PUT equals angle PTU equals gamma, right? So therefore I know that, so if I take this triangle, this is gamma, yeah? So if you take the triangle, so let me write it as angle whatever, UPT plus 2 gamma equals 180. So I can, now you can write it as 180 minus 2 gamma. So now in the triangle PQR, alpha plus beta plus 180 minus 2 gamma equals 180, and that also gives, right? Now, okay, I should really shut up with this. I have more problems, but this, I like this thing because there are like many different approaches, right? And it depends on, you don't need too much knowledge. As I said, if you know certain facts, like for instance, the alternate segment theorem, it's worth observing. Like for instance, if you do a direct proof, right? If you don't even need to use these facts. Like I said, you can try with congruence of triangles, and from congruence you can establish. Or you can bring in knowledge, like he said, right? Okay, that thing, it must be 90 degrees, right? But then we must write down that statement. Right? We are not doing things in a bit of a hurry. So I would say in each of those, write down those knowledge statements that we are talking about, and can we derive them, right? Who can derive what, right? Some children can derive actually. In fact, in this case, as it turns out, I mentioned the alternate segment theorem because this is a good place to actually do a proof of that. It's not very difficult, and the reasoning that's used in solving the problem, in fact, is actually sets up the proof of the alternate segment theorem as well, right? So it gives you quite a bit of scope for exploring further, and there are a couple of more questions, but in the interest of time, I should shut up now. So I have a few problems with divisibility also. So divisibility is another thing where there's a lot of fun you can explore, because almost always by the time you have done one divisibility problem, there are like 5 waiting for you next, right? So all I want to say in this is that, well, maybe we don't do all these Polya type problems, right? We don't do the motivation and forerunner problems. It would be nice to have some. It would be nice to have definitional problems. Unfortunately, even at university level, I don't see too many, problems where people perturb definitions and say, can I define it differently and what will happen, etc., etc. But that's very nice. And explorations. For explorations, as I said, one is thematic, but I feel that if we have a kind of database of problems, right, whole bunch of problems which are not intimidating, which are not very difficult, which are reasonably simple, close to textbook problems, but where there is some problem solving involved, right? And from there, we can lead to more and more problems. Hopefully, in each of these, ending with some non-trivial proofs or something where your, the knowledge component comes in. At that point, initially you start in a completely open-ended way without bringing in all kinds of heavy theorems and knowledge, but especially in geometry, there are, it gives tremendous scope for that. Trigonometry and geometry are places where you can do a lot of these, and ideally stop at a place where it becomes very hard, right? Where we don't know the answers, where we have some generalizations, where we make some conjectures. That would be. Because I feel that, we talked about it before lunch also, we don't have a good way of saying I don't know, right? But the truth is that we don't know a lot, right? So if there is a way by which we can actually explore, right? So the key word being exploration, right? So can we use, what kind of problem solving opportunities can we make use of? I've got a lot of problems to share with for anybody who's interested, which I will defend as to why I consider these as good problems, right? And I would like an argument of that kind, right? Why is this a good problem? No, this is a lousy problem. This is a great problem. This is what we want to do, etc., right? So if we can do that, and we can do that with children as well. I have done some of these discussions that I'm talking about, oh, this is not a nice problem, this is a good problem, with some children. As long as we are open to, all kinds of comments, there is no problem at all, right? That it's okay. And as long as we say it's fine to say I don't like this problem, right? I don't like this at all. I like a different problem, right? So with that, I think it can open up a lot, and some atmosphere of discussion and argumentation. How do we bring that about? I feel that problem books or problem collections can be very good ways of engaging with that. And there are lots of friendly problems. We can discuss more if anybody is interested. Thank you. Comments are welcome. Okay. No, this, as I said, is this is textbook questions. At least the couple of them that I mentioned were textbook questions. The one I will mention is the art of problem solving. It's called what? artofproblemsolving.com. You go on Google and say art of problem solving, you will get to that site. There is a very nice site where, I don't like all the problems, but that is really the discussion I want there, right? Why is it that I don't like this problem? There are some problems I like, and so on. There is another online resource that I like very much is the Math Kangaroo. This is, I think, from France. Yeah, I like the Math Kangaroo problems. Are you involved in? No. Okay. So yeah, so Math Kangaroo problems I have seen. Again, it's a mix, right? I like some of the problems. I don't like some of the problems, and it's okay, right? But you can pick up a lot of very interesting problems. And much more important for me is that these are sites where many teachers post, right? Many teachers post their own problems, discussions on what was their experience in problem solving. In artofproblemsolving.com, in fact, I like the discussions much more than the problems themselves that are given. There are many very nice discussions. So again, if you write to me, I can suggest this thing. There is a Russian, sorry? I don't know. Okay, sorry. Yeah, I don't know this. Yeah, so must be many more. I'm just only referring to things that I have seen and made use of. Shailesh Shirali's problem books I have made extensive use of in whatever discussions I've had. So those are, empty publications, really very, very, I would say, cheap, inexpensive that you can get. There are a couple of Russian problem books that are available online. I don't remember right now. I'm sorry, I forgot to write it down. But if you write to me, I can. Yeah? No, that is true. But the problem books that from Russian sources, but they're available free as e-books. So, but they're very tricky. Some of them are very, very tricky. But so the thing is to actually develop a taste for what you like. That's all I'm trying to say, right? In these things, it's not like one source, right? It's more like if you say, okay, this is the kind of problems I like, you can pick up them and work on. And if for teachers, what I would say is that we need, 2-3 different tastes, 2-3 different kinds of tastes, right? Problems that appeal to different tastes. If you can have a menu of that kind, it will be very nice. At right angles, there is a problem corner. How can I forget? I mentioned at right angles. I have forgotten now which are the. Yeah, that's available online as well. There is a problem corner where people can post problems. Please do post for at right angles. Yeah. Anything else? Okay, thank you.